So in the course of doing these book programs around the state, I had an invitation to do the first one in person since the pandemic down in Macon. They asked me to talk about the fall line. You know, I put in a lot of work, so I was hoping to get some more opportunities, and I really appreciate the chance to talk to AGS. And then on I'll be August 10th, I'll be in Columbus. So this slide is Columbus with a powerhouse and the rapids that once they took out the dam that used to power the powerhouse, and now they have this wonderful whitewater thing along the Columbus River Walk. So this is kind of one of the classic pictures you could have anywhere of the fall line. And so I'll talk about what the fall line is in a second. I'll just say a little more about roadside geology of Georgia, which most of you are probably familiar with in any case. It came out of the roadside geology series. It started in 1972 in Montana and Idaho, grew across the country with two-color editions with maps that looked like this, but great, interesting information. And then 2008, they started running full color editions that had full color maps. And we were fortunate to be in 2013, one of those. And so, of course, the name roadside is more applicable in places like Montana than it is in Georgia, where you just have a thin pamphlet if all you wrote about was what you see from the interstate highway system. But we fortunately have places like Cloudland Canyon and Tybee Island and Tallulah Gorge that we can tell stories about. So that's the idea behind roadside geology of Georgia. And so when I start my talks, I start nearly every one of them with this map from the book that shows the physical regions of the Southeast, which are also geological regions. And of course, the southern half of Georgia is in what we call the coastal plain, which is loose sediments, pretty much, not too many rocks, that accumulated beside the Atlantic Ocean, the Gulf of Mexico, as the shorelines shifted back and forth across this area. And the northwest part of the state, we also have sedimentary rocks, but they're much older. They were beside an ancient ocean that's now gone, and where it went was it slammed shut when Africa collided with North America and all the continents came together to make Pangaea. And slammed in the door at that time and shoved deep underground were the Blue Ridge and the Piedmont. And those rocks got changed by heat and pressure into metamorphic rocks. Some of them melted and cooled to make igneous rocks, such as Stone Mountain and so on. And so the fall line is simply where the edge of the sediments of the coastal plain lap onto these older rocks. And across Georgia, all across Georgia, it's onto the Piedmont. So it's pretty much onto pretty pretty hard metamorphic and igneous rocks. And the contrast with that in the sediments means that the streams that are crossing it are coming down and are coming off of rapids and shoals and so on and into flatter country. So not quite waterfalls everywhere, but we'll get to that in a little bit. And so I always like to overlay the geologic map on this. And a lot of people are not familiar that, you know, where you see ridges like this in the topography, then you see geologic units that correspond to them. And also, I, of course, point out that the actual, you know, the age range of these different provinces, with the much older ones in Northwest Georgia, the wide range of ages in the Piedmont and Blue Ridge, and then the much younger sediments of the coastal plain. And so we talk about, you know, to first understand why there's a fall line, of course, you want to know why these sediments are here. And you really want to go back to Pangaea. So this is Christopher Scotey's paleogeography that were packaged by an excellent teaching resource called TASA Arts Theory of Plate Tectonics. I'll be showing a couple of illustrations of theirs. But of course, when Pangaea splits up, actually the central Atlantic, the opposite Georgia, was first, and it spreads apart. And then the South Atlantic breaks up. You notice this kind of dog leg where Africa and South America split up in the South Atlantic. We have India comes in and runs runs into Asia, pushes up the Himalayas. But this is the last 300 million years or so. Well, actually, last 190 million years or so of plate movements. And so while that's going on, what you're seeing is this kind of a cross section. So here's Pangaea getting ready to rift apart. You've got the hot material coming up here. The area, land surface kind of gets domed upward. And then as it pulls apart, you get some of these basins that are dropping down as the crust starts to thin out in this area. And it continues to pull out and thin out the crust until finally there's no continental crust left at all. And what comes up is the hot material from underneath melts and cools off and makes oceanic crust and along the mid-ocean ridge. And so this process continues for a long time. And while this is going on, erosion is happening on the on the flanks of the ocean and piling up sediment. So this represents the sediment that piles up on the sides of the ocean. And so the ocean continues to get wider. And you develop a broad flat area called a continental shelf built on top of all that sediment. And then eventually you've got that broad flat area. When sea level rises and falls, you'll get a coastal plain. You'll get a plain like that, and sea level rise and fall moves it back and forth and so on. So the fall line, well, it's the surface expression of this boundary between where the sediments are sitting on top of old Pangaea. And so you can trace it along the map, something like that. And when you want to go see it in real life, this was a picture that we inserted into the AGS newsletter this month that Pamela Gore took a little bit west of Macon. And this is a place where the Cretaceous age sandstone is resting on top of, in this case, very weathered granitic composition, metamorphic and igneous rocks. And so if you slice through all this, you get a cross section that looks something like this that we've got in the book. And this, so you see that everything, you get younger and younger sediments at the surface as you go towards the coast until you get into the stuff that's been produced today by shoreline processes here at the coast. And underneath, you've got this tilted stack of sediments. And where the stack of sediments comes to the surface, that's the fall line. So in terms of looking at the bigger picture, you can actually trace this edge of the sediments of the coastal plains all the way from Texas up to New York. And the way I drew this line was I overlaid on Google Earth, this Google Earth overlay, which is the geologic map of the United States. And a lot of places, the green, which represents the Cretaceous age sediments, so about, anywhere from the 100 to 60, Cretaceous ends 65 million years ago, but a lot of this stuff is a bit older than that. And it's resting on top of this older stuff. But some of these younger sediments also rest directly on older rocks, even including in eastern part of the fall line in Georgia. And so that you can, again, like I say, trace this all the way up to New York City. So I'll zoom in on this little area right here. And so you can actually see this boundary between, this is the Cretaceous age sediments here. And these are the older rocks in New York City, like in Central Park, you can see outcrops of some of these metamorphic rocks in New York City. I found out after I titled the thing, I thought Brooklyn sounded, it goes all the way to Queens, but I thought Brooklyn sounded better in the title. Here is the Cretaceous. And what I found out was that I don't know there's any place you can go and see this at the surface there. There's this right here, this color is the glacial deposits that make up most of Long Island that basically were like a gigantic moraine that was left by the continental ice sheet that covered New England. But apparently there's some of that glacial material also covers most of this. So I don't know if you can see this in New York, but what they've drilled into is called the Cretaceous age Raritan formation. it's named after exposures right down here in Raritan Bay. So presumably you go down here, you could see some of this stuff. So anyway, my point is you may not see the actual fall line like that picture I showed from west of Macon right in New York City, but this is more or less where it runs out, where that runs out. Okay, so so you can do a little game of asking yourself about, you know, how the fall line influenced history by going through and naming capitals of places. Like, what's the capital of New Jersey? And that would be, let's see if this works. Okay. No, it doesn't want me to do anything but click it. Okay, so clicking works or not? Clicking doesn't work when I've got a pointer. Page down, page up doesn't work. All right. So, okay, now we get it. Okay, there we go. Page up, page down did work. Okay, so anyway, here's Trenton, capital of New Jersey, capital of Virginia is Richmond, capital of South Carolina, Columbia, capital of Arkansas is Little Rock, capital of Georgia is Milledgeville. Oops. Well, capital of Georgia was Milledgeville. So all these state capitals were arrayed along the fall line. And in addition, the nation's capital is on the fall line. So all these grew up on the fall line. And when you go through largest cities, all these large cities, New York, Baltimore, Wilmington, Philadelphia, are all large cities on the fall line. And then we have smaller cities like Rocky Mount, Tuscaloosa, and our three other Georgia cities, Columbus, Macon, Augusta. They're all on the fall line. And so what these cities have in common is they're all old. They're all pre-railroad because navigation was done by rivers, and you know, the transportation was done by rivers, and you got to this edge and you had to at least portage to get into a smaller boat or something because you ran into rapids once you got on the harder rocks. So you know, early cities around New York in the 1600s, early 1700s, you have moving down into Virginia a little bit. Georgetown was founded in 1751, and Washington, D.C. later incorporated Georgetown. It was a fall line town. And then we get on down to in Georgia, we've got Milledgeville founded in 1804. Augusta was already there. Tuscaloosa is pretty old. Little Rock over here, 1821. So all these early pre-railroad cities were founded along the fall line for the reasons that I've mentioned. Now, when I went to talk to Macon, I said, but actually, you could consider Macon as founded 950 AD because Macon is actually the site of a pretty substantial sized city that the Native Americans built, and they built mounds. And if you go to these three mound builder parks in Georgia, you notice their locations may be controlled by the geology to some extent. So, you know, I-75 runs right by these two mounds, and it's probably the ancient trade route. Routes did the same thing to get people from the ocean, Atlantic Ocean up to the Great Valley. You know, these were key places on a trade route. And the other thing you can look at as far as geology goes is we put our geologic map on there, and then I'm going to convert this to a sort of a chemical map so that all the limestone will be one color and all the quartz-rich sand and quartz-rich rocks will be another color. So we do that, and the limestone and the dolostone, the carbonate rocks, become blue. And you notice that all these are also close to where you've got a lot of carbonate rocks, which is what often makes good farm soil. So there's probably a connection there as well. So that just having made the historical connection, let's just walk ourselves through geologic history and see how early can we start thinking about this fall line location being determined. And we can really start all the way back when we had a supercontinent called Rodinia. And Rodinia was 600 million years ago. It starts to split up. So let's see if I can operate. I may have to, let's see. Yeah, I may have to undo my pointer to operate I think that's what I have to do. Automatic, yeah, okay. So I can operate my animation. All right, so we've got this supercontinent. It doesn't look like much of anything just yet. but now we're going to pull it apart. And we start to see that's Greenland there. That would be Hudson Bay, Great Lakes. Those two didn't exist back then, but they're good reference markers. But you go down the east coast of North America and you're missing Florida right there. So Florida was actually on the other side of the ocean at the time. This is Northern Europe here. Um, and um, and then this is with Scandinavia. And we get a little chain of islands that rips off of the coast of, this is South America upside down, rips off the coast of the other side and comes in with Scandinavia and collides with North America. And now we see here's South America upside down. This is Africa. And here's Florida and South Georgia tucked in. And they're going to come in and run in as well and come in. And then we'll be back to the Pangaea that I pointed out earlier. And I'll move that forward like this. Okay, so we've already seen all this part. Okay, so my point in taking you back to that history is that Bill Thomas of University of Kentucky has thought about how Rodinia split up as a control on some of our present geology. And the key point in this, you remember we noticed that dog leg in the Africa, South America, and a dog leg in the mid-ocean ridge. So the mid-ocean ridge comes down here and then it jumps over on a couple of these fracture zones, which are called transform faults when they come in between the two segments of the mid-ocean ridge. And so this is part of the initial geometry of how the Pangaea split up. And so similarly, going back and looking for the geometry of how Rodinia split up, Bill Thomas drew something like this, okay? And so he has the Alabama-Oklahoma transform fault, kind of analogous to that thing that offsets at South America and Africa. And that partly, that controls why, to some extent, why the fall line makes this big embayment here into the Mississippi Valley. But in addition, you can notice that his area of rifting gets closer and closer to the present coastline as you get up towards New York. So this same narrowing of the coastal plain is also a feature that you can trace back to the breakup of Rodinia. So this is my favorite map to show what the fall line is and to show what this blanket of sediments of the coastal plain looks like, because he not only shows the edge of it, the edge of the gray, but he uses darker gray colors to show the thicker areas. So you can see how thick the sediments are down here. And all these black dots, I believe, are salt domes, many of which are oil prospects or oil fields. And so one of the reasons that this area is so oily has to do with the fact that that things got down so deep, that the sediments got so thick here that the organic material was able to convert into hydrocarbons. And so you're looking at something like this down here. Anyway, you can also see that it shows that the older rocks that this is lapping onto, where there's sedimentary layers of flat-lying sedimentary rocks, he shows them thickening also as you get towards the area where Africa slammed into North America. And then this blue is showing the area that was crumpled up as that happened. And this area is showing the area that, with all this speckled pattern, is showing the area that got heated up and metamorphosed and so on. So he really shows with one map, he shows all the damage that Africa did. He shows the edge of the coastal plain sediments. And you can see how the fall line did all that zigzagging around Texas. So that's where I got some of that from. But also, he shows what happened after that collision. And it has to do with these, what he calls post-orogenic deposits, the upper Triassic basins. So these are the basins. And this is where the brownstones, there are a lot of red sandstone beds in there. So the brownstone apartments of New York City and these northeastern cities are made from stuff from these beds. But it's such a pretty building stone that they brought some of it down to Georgia. So this is this is with Bill Wagner. I've been several years doing and with co-sponsorship of Atlanta Geological Society several years. At the Atlanta Science Festival, I've been offering this walk and looking at including building stone and teaching geology. And so this is a really good place to stand and teach about this pulling apart these basins, because here's the red sandstone that was quarried from some of these pull apart basins. And this black rock is diabase that came from something called the Palisades Sill, just opposite New York. And this is part of the magma that came up in the same pull apart episode. Down here, it came up in long dikes that are shown here as red stripes. So just cracks that got filled with magma that trend across the countryside. And up in New York, there's actually enough of it to quarry and make this black stone that's used in a lot of memorials, including this one to the people who died in the Air France crash, who were art patrons. So anyway, so we have this story about the pull apart, and it turns out that there are just after you step out, just south of the fall line in Georgia, these kind of basins are also there in Georgia. They're just buried under the coastal plain. They have been drilled into, so these are cores that we have pictures of in the book. And this is where these basins are in the subsurface. And this is that same cross section I showed. It was 40x when I showed it to you before. Now it's only 10 times vertically exaggerated. But we're showing that there's these pretty deep basins of sediments that are actually underneath the Georgia coastal plain, just south of the fall line. And so this actually, I was always taught this was part of the pull apart that preceded the Atlantic. But there's another way to look at this that Jack Ma of Auburn has been pointing out lately in an article in Geology, as well as in a talk that he gave at the recent GSA, Southeastern GSA meeting, that basically, here is that same edge. This is the area where the Triassic basins are under Georgia, and this is the area where the Piedmont is uplifted. And he draws a cross section across it and says, that these faults that are help bound the South Georgia Basin certainly could be what we associate with the collapse of a mountain range. When you pile up a mountain range like the Himalayas, for example, when you uplift the area because the crust is thickened up, some of the rocks on the surface, they don't simply erode, they actually slide off on faults and so this concept would actually put the pulling apart beginning in the Permian time, as early as about 195 million years ago. I'm sorry, 295 million years ago, preceding the beginning of the Triassic. So maybe these South Georgia basins and some of these Triassic basins began as collapse of the uplifted mountain range. So moving along, now we're to 65 million years ago when the asteroid hits right here and causes a lot of extinction, and also sends tsunamis that have been found in deposits on the Texas coast, and it's Shell Bluff in Alabama over here. And I believe Scott Harris led a Georgia Geological Society trip to see some evidence of these same tsunami deposits over here in South Carolina. We haven't got them in Georgia, maybe because we don't have the right erosional. This area that's along the fall line was too far out of the water at the time to preserve a tsunami deposit. But when the asteroid hits, we get these tsunami deposits. But anyway, you notice that the shoreline then pretty closely resembles the present fall line. And it's easy to tell somebody the fall line is an ancient shoreline. And you can certainly go to places like Columbus, and this is a place where I'm looking at these ghost shrimp burrows, which are what I would see today if I cut down in the sand at Tybee Island underneath these chocolate sprinkle looking things that are actually fecal pellets. And so these are burrows that indicate that this is a beach environment that I've got my hand on outside of Columbus. So certainly there was shoreline here at one time. The problem is that every place you stand is probably a different, slightly different age shoreline, and you can certainly see that you know, it's the shoreline in Columbus, the fall line in Columbus is late Cretaceous age stuff, somewhat younger late Cretaceous around Macon. Once you get over past Milledgeville, you're into stuff that's much younger, getting around 50 million years or so. So each of these points might have been a point on a shoreline, but they're different ages. Okay, and another interesting thing about this is that, you know, when you think about the ancient shoreline, you say, oh, well, sea level was up that high and it left this was the shoreline. It's also interesting to know that the surface of the land has uplifted in more or less in different places. So this red arrow right here, this is a Google Earth topographic profile. You draw a topographic, I drew this line in Google Earth, and then I asked for a topographic profile. And this is what I got. And this red arrow right here is going to correspond to this line. You see the 1838 feet over here. And when I play this animation, the red arrow up here will move and the line will move. And so you can see that now we're up in, this is now we're crossing the Mississippi embayment. Now we're coming down, we're coming into Georgia. I'll stop it right here for a second. So it's saying that right here, the elevation that the Google Earth profile crossed was 416 feet above sea level. But you notice that over in Texas, it's been uplifted quite a bit more. So there's been some disturbance to this shoreline. There's certainly some uplift. Once you get down, less and less as you get towards New York, that it's more at the original level that it must have been at. Okay, so let's see. Let's see if I can page down. There we go. Okay, so in terms of finding good pictures of the fall line, I was with my cousin and her son up near Washington, and here's the National Park Service has conveniently put us a picture that says Potomac River fall line, but we're more than 10 miles from the nearest coastal plain strata, so geologists would not consider this the location of the fall line. It's certainly a beautiful waterfall, but it's really not, you really can't call it the fall line. And just to demonstrate that, here's Google Earth again. I'm going to overlay the geologic map on it. And so Great Falls of the Potomac. Let's see, let me go back to my pointer now that I've gotten past that animation. Yeah. So here's the Great Falls of the Potomac. Here is the edge, runs through Rock Creek Park, if you know Washington, then runs through Georgetown. And the C&O Canal actually begins right at the fall line. The park begins in Georgetown, and you're still walking on beside this canal right there at the Great Falls of the Potomac. It has to go through quite a few locks to get up there. Okay, so not the fall line there. All right, then there's this in the New Georgia Encyclopedia, which is a wonderful resource that helped us with the book. And there's a wonderful article by Mac Duncan, who many of you may know, in the New Georgia Encyclopedia. But for some reason, they've got this picture stuck in here, which is nice and dramatic. But High Falls State Park is more than 30 miles from the nearest coastal plain strata. And Mac didn't put that picture in there. I've pointed it out in the past, but nobody seemed to worry about it enough to, it certainly makes a pretty picture. Nobody has changed it. So not the fall line. Okay, so, but in the Texas Hill Country, indeed, we have the Cretaceous age conglomerate sitting here at Pedernales Falls over Pennsylvanian age limestone. And so somewhere in here is that same boundary between that we drew as the fall line. But even there's a little bit of a question mark because you know, you look at the big picture here, and the edge of the hill country got down here by Austin and San Antonio. And so what's going on is, you know, indeed, this is the edge. The Paleozoic rocks here are shown in pink, lower Paleozoic, I guess, but I don't know, Pennsylvanian should be. Anyway, never mind. Enchanted Rock, if anybody's been there, it looks like a pink stone mountain. but in about billion-year-old rocks of the Llano uplift. And this is the Cretaceous sitting on top of it. But the real topographic relief is along this boundary right here, which is actually a fault called the Balcones Fault. But the reason the topographic boundary is there is that this harder limestone is pulled up, it's a normal fault, so is in the upthrown block, and in the downthrown block is softer sediments. So that's the edge of the Texas Hill Country. So really, you'd want to call that the fall line, except it's not geologically the fall line. So it's kind of hard to get yourself right on the fall line and show you a waterfall. So this is the best we can do in Georgia. This is the rapids at Augusta, near the canal in Augusta. This is in Milledgeville. This is the one in Columbus I showed you. Macon, not much in Macon, just a little bit of rapids right there by this. It goes by this rock. Macon doesn't really have much of a good rapids at the fall line. So seeing this, I took a minute. I had Google Earth draw me some topo profiles 30 miles south and 30 miles north of the fall line at these places in Georgia. Then I kind of summed it up with these lines. And you notice that there's not much of a difference when you cross the fall line in terms of the gradient of the stream. By the way, if you're stopped at these are the dams and the lakes behind them. That's why it does these steps here. But the one place where there is a natural slope at the fall line is at Columbus. There's a good slope there. And hence, the most dramatic picture was taken there. So you also hear that the fall line can be up to 20 miles wide, and that, you can't quite get to high falls with that, but you could say, well, maybe the Great Falls could be considered on the fall line. But I think what we mean when we say that fall line is 20 miles wide is that if you go from, this is the northernmost point of the Eocene sand and clay north of Milledgeville. And this is the, corresponding oceanward most point of the igneous and metamorphic rocks that we're resting on. And so that distance is there's 10 miles there. This distance is about 20 miles. So I think that when we say the fall line could be up to 20 miles wide, we're talking about that kind of situation, from there to there, about 20 miles. So one other thing to throw in is the fact that you've got some very smooth places in the Piedmont, and you've got some pretty hilly places in the coastal plain. So hilly place, you come out of Macon on I-75, you are climbing out of the Ocmulgee Valley, but you climb coming in on I-75 coming out of Macon into some hilly country. And correspondingly, there's this really flat area here, which actually extends all the way up to Atlanta. Hartsfield Airport is on the flattest area around Atlanta, which is in the same watershed. It's the watershed of the Flint River. So why is the Flint River running through such a flat area here? And there's an answer to that, because it's got some work to do before it can come down a slope. It's got to grind its way through these quartzite ridges. In fact, if I go back a second, this quartzite ridge, this is Pine Mountain. And it's all Hollis quartzite, very resistant rock. And so the Flint River is grinding its way through that. This is where the Flint River cuts through here. And upstream from that, it's perched up there. It hadn't been able to cut its base level down low enough. So you got this very flat area that extends all the way up to Hartsfield Airport. And then you got, areas like the Fall Line Red Hills, like the Fort Valley Plateau. This is the Fort Valley Plateau here, that are kind of elevated areas in the coastal plain. So because there's been some uplift, and because we've got geology with some resistant units, then we do have some hilly areas in the coastal plain. And this is kind of interesting. The Fort Mountain Plateau is held up by clay. You think of clay as being not very resistant, but compared to loose sand, it is pretty resistant. So some of that clay is in the Clayton Formation. Same thing as the Caps Providence Canyon. There's also ironstone in it. So it's a fairly resistant unit. Okay, so so back to this idea about raising sea level. If we rose sea level today to, in other words, melted all the current glacial ice, the estimates are that the oceans would rise about 230 feet. So that on our previous profile puts us up about right here. And so you can see that it's not until you get up to the northeast. I can run the thing. I have to get, let's see, I'd have to get back to get out of my pointer, but you can take my word for it. How about that? That this point here is about right here in North Carolina, where you start to see actual waves crashing against the fall line is sort of in this area. So all this area down here presumably has had some uplift, okay, since the time that these marine sediments, Eocene sediments and so on were laid down. So what about uplift? What about uplift since 50 million years ago? Well, this came out the same year as our book, was this study by Sean Gallen that shows that there was an argument for there having been uplift as recently as the Miocene epoch, which is 23 to 5.3 million years ago, in the Southern Appalachians. And so I went on a field trip 2 years later, and by that time, Sean Gallen had gotten his postdoc in Switzerland, so he wasn't able to lead the field trip. His advisor, Kurt Wegman, led the field trip. And we were down in this place, down at the in the Colasaja Valley, where there had been some really devastating debris flows. And the point was that this is like you would see in an area that has active uplift, to have areas with debris flows coming down. And we went on up the Colasaja River past the this is called Dry Falls for some reason, and then all the way up to the area around Highlands where it's actually pretty flat. So this same river up running through flat country up at the top. So the idea is that an area that had been planed down flat has been uplifted in pretty recent time geologically. And so this is part of their study, is showing the digital elevation model of the area, and asking how much was scooped out by erosion and how long would that take, essentially. So they took how much had been scooped out by erosion, they measured it, they estimated by what we know about rates of erosion, and they came up with a time as to how long it would have taken. And they said, well, this area around Highlands was much lower elevation this long ago, and it's been uplifted since then and eroded out. And then they back that up with this information about the age of the sediments you find if you're going along the mid-Atlantic coastline. You have this much thicker area of Miocene age sediments. This is not a worldwide feature. This is an Atlantic coast feature related to our Appalachians. And actually, in the Gulf of Mexico, you also find this, and there are also heavy minerals that point to the Appalachians as the source of the material. So I went on another field trip. This was the reason I missed the field trip that Scott led over to the tsunami deposits in South Carolina, was that the same weekend, the Carolina Geological Society was holding this field trip. And this is Kevin Stewart and his student, Jesse Hill. And so these are some illustrations out of the field trip guidebook. And so one of the things that a lot of people have noted is that when you follow the high elevations across the Southern Appalachians, they're in the Blue Ridge and the area that was most thickened during the collision, presumably, down in Georgia, all right, and in North Carolina. But once you get up to West Virginia, they're out in the Appalachian Plateau province. So the area of highest elevation crosses the ancient boundaries that were generated when that collision took place. and not only that, but when you take this highlands area and you compare it to the big map, and we see that swing in the fall line, it really is wrapping itself around something that Kevin Stewart called the Selma Arch. So that this wrapping that involves rocks as young as Eocene, certainly in this bend, is a young enough feature, at least in part, to be related to this uplift of the Blue Ridge. So in Jesse Hill's dissertation and in the guidebook, he had this illustration. And what the red areas are, you remember that area in highlands that was so flat? These are areas that are at high elevation but low slope. So these are uplifted, relatively flat areas. And again, they're doing this trend across the grain of the geologic provinces. And then, of course, the yellow are the slopes coming down from those areas. And so the conclusion was that you had an area that was more or less planed down, more or less flat before this more recent uplift. So when you think about what can cause mountains to be high, the classical explanation is that this is again the tossograde plate tectonics, a cross section through, let's say, today's Himalayas, and you have this doubling of continental crust that thickens the crust, and it's sort of like if you've got an iceberg that is buoyant on water. Well, this thicker continental crust is kind of buoyant on the soft, if not liquid, but soft asthenosphere, this part that's deep enough and hot enough to flow. And so it's kind of like an iceberg sitting up here with an area that's going to be up high because it's got this lower density root underneath it. But one difference with an iceberg is that as this mountain range is forming, there's magma continually coming up. These are intrusions of magma. Sort of Stone Mountain would be an example of something like this, where something melts deeper down in the crust and stuff comes up. And the magma that comes up is the lighter, less dense minerals melt first. So you're left with denser minerals. So I was fortunate to be in the Alps, the Italian Alps, just before, 2019, and this is rock that is almost all garnets. It's interpreted as what was left over near the base of the crust when the lighter materials all melted and made it to the surface. And the reason this is at the surface is that the collision between Italy and Europe has sort of made a big kink in the whole system called the Ivrea zone. And so this is kinked up to the surface where we could touch it. But this is extra dense rock. So go back to our iceberg situation, and we say, well, what happens if you get this area that's denser down here, that's extra dense rock? It's not going to want to hang around with the rest of the iceberg. It's going to want to drop off. And so when it drops off, then what's going to happen up here? This is going to pop up. So you can have this delayed effect called delamination of the dropping off of this denser stuff down below. And the lighter stuff at the top is going to pop up. And you get these delayed uplift episodes due to this delamination phenomenon. Okay, so that brings us to this illustration that Jesse presented, which is showing the crustal thickness. And so the places that are actually thickest under the Appalachians are not where the highest elevations are. Here's the thickest crust. Here are the highest elevations. Okay, so what could be going on? Once you get up to here, there's really no correlation at all between thick crusts and high elevations. As you get down here, there's a little more, but we got this low elevation and thick crust. Okay, so how do you explain something like that? So going back to the iceberg, what if you just have sort of segments of it breaking off at a time? So in this case, you have a northern end of this piece that has come off recently, and recently being Miocene time or something like that. And when it came off, then the material above it popped up. But adjacent to it, and you've got to flex this iceberg more than icebergs really flex, but adjacent to it, you've got stuff that didn't drop off, and therefore it didn't pop up, okay? So you got one area popping up. So the area with the thicker crust, and this would be like Northwest Georgia, for example, has very thick crust. It's just, it's low because this piece hadn't dropped off yet, and this hadn't had a chance to pop up. And when you're over there under Mount Mitchell, you know, the piece has dropped off and this is popping up. So that's that general idea. This drops off and it pops up. So going back to this, Jesse drew his profile line along here and used the seismology data of this guy, his colleague at North Carolina, Burke Berryall. And Burke, actually, because of the Mineral Virginia earthquake and people looking around for explanations for why this big earthquake could rattle everybody's teeth in Washington, D.C., this made this is the Daily Mirror in England that I captured this from, including Burke's picture and all that. Giant chunks of the Earth's interior falling off and causing earthquakes in the USA. Look out! Look out! So that's sort of what that's the theme of the idea. But anyway, so that profile of the line that I drew you goes through here. And indeed, he finds that in the northern, this is under Mount Mitchell, say, and this is going up towards West Virginia. And he finds that there is this colder, denser slab down at a certain depth. And it hasn't dropped off as far down yet in under Mount Mitchell as it has under West Virginia. Okay, so it's at a shallower depth there than it is here. So it's kind of peeling off from north to south, perhaps. And when you plot this on this drawing a map at this depth, you see that where this actually lines up, it lines up very nicely with this highest elevation area that Jesse was pointing out. So, interesting ideas about what might be producing this Miocene age uplift of the Southern Appalachians, which in turn translates into the sort of the current bend, the last bend in the fall line. So I have talked to you about Brooklyn, Texas, okay, the Asthenosphere, and the Cambrian. The Cambrian being when Bill Thomas is showing that the early breakup of Rodinia gave us part of the outline. The Asthenosphere we were just talking about is the soft material underneath that things are dropping off into. But I haven't talked about Alluvium and Anthropocene yet. So I've got to get a little bit down to the more nitty gritty about the fall line. This is one of the things some people equate the fall line to the gnat line, which is you get down in the coastal plain, you got a lot more insects to swat at, okay? And what's all that about? This is Pam's write-up about the gnat line from our book. And you can sort of connect that with the fact that on an aerial map, aerial picture like Google Earth provides, you see that where rivers cross the fall line, there's a sudden widening of the floodplains. You see these wide, in this case, forested floodplains. That's why they're so green. But suddenly the floodplains get wider. This would be down by Milledgeville, Macon, not sure what this one is, but by Columbus, you get these wider floodplains. And if you can actually, you go to my georgiarocks.us websites, you can pull down this Google Earth overlay. And what I did was I took the USGS overlay of the geologic map of Georgia to overlay on Google Earth, and then I recolored everything and gave it a legend. And this is too small for you to read maybe, but this is Quaternary stream and wind deposits. So this is the Quaternary stream deposits, river deposits, and occupying these wide floodplains. Okay, so I promised the Anthropocene, and so where we're talking about a period of time when humans have had an influence on geology. And so I found this reference in an article by somebody at I think it's at USGS, um, and um, and basically that said that when there was deforestation and poor agricultural practices, as in cotton, that they cut down all the trees and they grew cotton up here, you got a lot of erosion off of this. And where did all its sediment go? Well, it came down, it aggraded the streams, so it made the streams flatter and filled in with sediment, and that caused them to spill over and widen their floodplains. So some of these wide floodplains may be the effect of human impact. And there's the other side to it, which is that since this has grown back, you're now starting to see incision into some of this old sediment that got piled up there. And you get floodplains and terraces and all that. And it also, you might have noticed around the Atlanta area, you'll notice, but I'm sure it's got the same in Macon and other places. If you've got stormwater runoff, you get more channel incision too. So we're continually reshaping the landscape. So I think I wrote that, the latest rainstorm can alter the fall line a little bit. And I think that's probably true. So, so that's the end of my talk. I just want to mention that if you want to go to or send somebody to some of the programs I do, I've got some lined up, in-person programs lined up that you can find listed here, and you can just subscribe to my e-newsletter. And so we have the Columbus that I mentioned. I'll be with Leslie Edwards, who's the first author of Natural Communities of Georgia. We paired up for several years doing a program on top of Brasstown Bald about the relationship between the geology of the Brasstown Bald window. It's a geological window, and the natural communities, things that live there. It's kind of an island in the biogeographic island at the same time. So October 9th, the next day each year, we've gone over to Anna Ruby Falls and done a walk there, which is just outside of Unicoi State Park near Helen. And then I've just recently agreed to do try to research and understand the origin of the gemstones that you'd find within an hour's drive of Ellijay. There's actually emerald, as in dark green beryl, that's sort of gem quality. There's gem quality garnets have been found. There's even gem quality rubies and sapphires that have been found within an hour's drive of Ellijay. So people are interested in those kind of things, and try to teach some geology around that. And then the Benton McKay Trail Association is doing a walk fest in Helen, and I've got a Raven Cliffs walk on November the 12th. So those are things that I've got lined up. And if you go to this website and go subscribe to my e-newsletter, you'll get about once a month or less often, you'll get a reminder. And so again, that's the website. When the e-newsletter comes out, that's the main thing I use Facebook for, is just to mention that the e-newsletter came out. But we do have a Facebook page, and Pam updates it as well. So that's the end of the slideshow. So I'll unshare and see what kind of, if there are any questions. So I see one from Jim Bowman: what characterizes diabase intrusions at the fall line? Well, I'm not sure. I'm not sure, Jim, are you asking why did I include diabase intrusions in discussing the fall line? I think I was, they're interesting, and they kind of relate to the pulling apart of those pull-apart basins, which certainly line up along the fall line. So I think the Triassic pull-apart episode is part of the story. But I don't know there's anything special about the diabase intrusions when they cross the fall line, other than that they get buried under sediments, that I know of. If anybody else knows anything, or you want to clarify that, that's fine.
I had a comment. This is John.
Yeah.
So were you aware of the there's like a sediment trap like north of the fall line, like in the Warm Springs area? Dave Prowl with USGS had studied that, and it was, I believe it might have been Eocene age deposits that were up way up there in that area north of the fall line.
Yeah, yeah. Okay, here it is, page 255 in the book. Paleocene age sediments
Paleocene,
exposed
okay.
north of Pine Mountain. I've got a little picture of them right here. Down a dirt road a little bit west of Warm Springs. And yeah, so, you know, the present trace of the fall line is certainly have people, it's open to interpretation that, you know, since there's been an uplift that you could have had a continuous blanket of these sediments that came up farther up onto the Piedmont. And so it could have been a part of that continuous blanket, or it could be just its own little local terrestrial sediment. I don't think anybody said they're marine, but certainly, you know, the present position of the fall line is an erosional, is related to erosion, and that uplift that I think that Selma Arch that Kevin Stewart presented is really responsible for where the fall line sits right now as it goes through Georgia.
I have a question for you, Bill. Okay.
Yeah.
Could you relate the uplift to the myriad, albeit very low scale earthquakes that we record in Georgia?
Yes. There is. In fact, I've done another different talk that I actually borrowed those slides about with the iceberg and all that stuff from that takes in also the East Tennessee seismic zone, because the places where Bob Hatcher went out with funding from the Bob Hatcher University of Tennessee went out with funding from the Nuclear Regulatory Commission. After Fukushima, there was a bunch of funding to re-examine the earthquake potential of areas, and he went out and found actual faults in the East Tennessee seismic zone that have been active over the last, 10,000 years or so, and especially exposed in shorelines of places like Douglas Lake and Tellico Lake and so on near Knoxville. So I went on that field trip when GSA was up in Knoxville, and the place where all that is best documented and where the earthquakes, sort of the center of the East Tennessee seismic zone that extends down into northwest Georgia, is also coincides with the steepest edge of the western Blue Ridge. So like Mount LeConte sits as about 5 miles, and you drop about 5,000 feet from Mount LeConte going down towards Gatlinburg, and it's so the uplift of that, certainly could have at least activated those some zones of weakness that were probably there earlier, and so yeah, that may be some relationship to the East Tennessee seismic zone. And actually, on that same field trip that Jesse Hill did some work on the north edge of the Grandfather Mountain window, and he thinks that fault, that the north frame of the Grandfather Mountain window is very straight, and he thinks that is a fault that is a modern uplift, that has modern uplift on it. That's actually that edge that runs through Boone, where Appalachian State is. So that was part of the field trip, was to look at that.